Good afternoon, everybody. My name is Asfandyar Kuhi, and I'm Simulation Product Manager working with Waljan Belgium. And today's topic, we're talking about analysis of beam structures. All right, first let's have a look about the objectives and what we're trying to cover. First, we are going to the finite element analysis method, describing it, looking at what mesh look like and what is the element definition. And we specifically focusing on the elements by going over the quality and types and explaining different type of elements. And as we are doing analysis on the structures, our main focus will be on beam elements. So we're defining what they mean. We're looking at the cross-sectional properties, joint definition, and the methods for detection of the joints. Different type of loading on the beam elements and post-processing option. And also we highlighted a special, let's say, situation when the beam elements can be converted to truss elements and looking at the difference. We will accomplish our, let's say, educational introduction with practical case studies, where the first let's say case study is purely considering beam element on a structure which is a conveyor, and we're trying to understand how we can define the beam element on such a structure, looking at the practical ways of joints calculation and modification on number of the joints, and condition, mesh options, and post-processing. And we then continue on introducing a very, let's say, important aspect of doing any structural analysis. Well, we might find it is not always practical to have all the components in an assembly as a beam. Therefore, we have to have a mixed approach. Well, we're using solid, shell, and beam elements all together. And the case study is a particle separator. We will looking at how we can manually assign different element type, looking at the mixed meshing approach and bounding contact sets, and also looking at the beam diagram. All right, so with that introduction, let's first go to the finite element analysis, which is a numerical technique of solving field problems describing by set of partial differential equation. In order to do any finite element analysis, you have a CAD geometry which needs to be converted, or we call it discretized, to a finite element method. For that purpose, you need an element, well, it could be a triangular shape, or let's say brick shape, or tetrahedral shape, or any other shape with some nodes on it, and put series or network of those elements to your CAD geometry and represent your CAD geometry with that network. So a model which is being converted from a CAD to the network of elements called FEA model. Different element type, they have different, let's say, advantages and disadvantages, which we are not focusing on that one. Brick elements or tetrahedra, but what I would like to, let's say, highlight at this point is that in SolidWorks, we are just using triangular shape, not a brick shape elements. All right, so since we have created that network of the elements, we are ready to solve the FEA model. Well, basically at any nodal, let's say, location, we are simply solving an equation of force equals to stiffness times displacement, which is very, let's say, similar to a spring under application of the force. So initially force 0, and then if you apply force F, displacement would be X. So this is exactly when you are applying a force to a body component, or let's say an assembly, that is exactly what is happening in a very simplified term. So what we know at some nodes or some points, we know the force, we are searching for displacement. So initial outcome of doing this solution is displacement, and from the values of the force and displacement, we can get into stress and strain, let's say, results such as normal stresses, shear stresses, principal stresses, and etc. So in FEA, this is the equation we solve, and this is what we get. But what we highlighted in the beginning was we need to convert our FEA, our CAD model to an FEA using elements. The first, let's say, division I would like to make here is about the quality of element. We can have the first order, or what we call it in SolidWorks as a draft quality mesh or draft quality element, which might be a linear tetrahedral element or a linear triangular element. Well, you might have 4 corner nodes and 6 lines, or just 3 corners and 3 lines. That is going to, let's say, placed and divide your CAD geometry and connect them together, and you simply have a mesh. These are very simple elements. We need a lot of them to have the best representation. Imagine if you have a curve shape and you would like to present a curve with a series of straight lines. As much as the straight lines are small, you have a better presentation or estimation of the curves. This could be improved if we simply increasing the order of element. Let's say second order, or in SolidWorks we call it high quality mesh. It could be in a form of parabolic tetrahedral solid elements, which is defined by 4 corners, 1, 2, 3, and 4. 6 mid nodes, 1, 2, 3, 4, 5, and 6. And also series of straight line. Or in a simpler way, we can have a parabolic tetrahedral element. So as we said, the first division of making elements, either it's a draft quality or high quality, first order or second order. More of these elements are required to represent the best result of the CAD geometry curves, less of this required to represent. And same time, computational time is more here as you have more nodes, less as you have less nodes. Okay, now let's go to the element types in the term of the category of usage or the application. If you have a solid model, then you need an element which is look like a 3D element where it can represent your CAD geometry in X, Y, Z direction. You can see this is what we have introduced up to this point. But there are some situations which we have a thin fixture geometry, or let's say sheet metal geometry. Well, one dimension, which usually its thickness, is much smaller than the other two. Therefore, if you need to represent such a CAD geometry to an FEA, you need to use a very small solid element to sit on a thickness and then extrude it through the length. That might generate a lot of elements, and it takes a lot of time to solve. From the theory, we can prove that if you are putting series of 2D elements, either high quality or low quality, and looking at the top or bottom face, result, stress, strain, or anything else that could be propagated through the thickness, and looking at the other aspect of the stress, like membrane, like top face, bottom face, and etc. That could be again extended to the new area, which if you have a structural, let's say, series of members adding together and creating a frame like that, looking at the cross-section, dimensions of a cross-section is much smaller than the extrusion lengths. So we can represent these structures using 1D elements called beam element. So this is the focus of our webinar today, looking at how the beam elements are working, how we can assign them, and how we can generate the result on them. Okay. As we said, beam elements are another class of structural elements. They are one-dimensional. And since you can assign, or all the cross-sectional characteristic of that, let's say, structural member are considered during the derivation of the stiffness matrix, like K value. Remember, we said we are solving F equal to Kx, and K is stiffness. In this case of the beam element, all the cross-sectional properties of the beam are going to be used to update that stiffness matrix. Therefore, we can simplify our CAD geometry significantly and save a lot of time, not by going through the thickness or direction 1 and direction 2, and simply we get a very accurate result. Therefore, using any beam elements, you are going to represent your structural member with a line and 2 joints created at the end, and you are going to tell the software how your beam elements are joining with that joints, and also the cross-sectional properties which is going to be assigned to that. Terms of cross-sectional properties and joints are what we are going to have more talking about in the next slides. But one very important thing before we move in is how we can understand if a structural member is appropriate to be modeled as a beam. We're defining a parameter called slenderness ratio, which is the ratio between the length of the beam and largest dimension of its cross-section. If this ratio is more than 10 times bigger, then we are happy, and all our approximation as let's say beam elements are very accurate and really have minimal effect on the results from our study. One other note I would like to add is we can have tapered beam, like what you can see in the figure. Your cross-section would be the same shape, but it might be smaller or bigger when you are moving along the beam axis. This is also can be considered, and simply all the cross-sectional variation is also getting considered in our studies. The other thing is if you have curved shape, you are going to model this with a series of straight beams all connected together. There are some situations that we can't use beam elements if your structural member has a different cross-sectional shape at the end and the beginning. So it's not the same shape. This here we had the same shape, but here we don't. If you have any twist along its length, if one end face is not planar, you have a curvy shape. If slenderness ratio is less than 10, if you have a irregular cut through your beam, let's say structural member, and if at one end you have just a straight line or very small cross-sectional face. These are the good examples where you can't really use beam elements. Other than this, if you have curve shape, if you have taper shape, or a straight structural member, you can simply convert it to a beam. They have joints and neutral axis. Okay, now let's go more into the detail of cross-sectional properties. When you have a beam shape like this, like an L shape, and you create this geometry using our, let's say, weldment module, all the cross-sectional properties are automatically calculated from the solid geometry because it's all geometrical factors. Those factors, as you can see in the figure, are torsional constants, distance from the maximum shear, shear factor in direction 1 and direction 2. Well, it is all calculated, and you can looking at them, or if you like, you can overwrite them. Let's clarify one thing before we move on. When we're talking about direction 1 and direction 2 in a setup or in a result section, we're talking about longest side is called direction 1 in your beam cross-sectional properties. And also the direction which is perpendicular to direction 1 is called direction 2. So we always keep in mind the longest length is direction 1 and perpendicular to that one is direction 2. So as we said, cross-sectional properties is all geometrical information. Well, SolidWorks will automatically calculate them and show you. You can override it if you have a specific, let's say magnitudes or values you would like to put in this section. Second thing we have introduced about the beams is joint. A joint is identified at the free end of a structural member or at the intersection of two or more structural members, as you can see in the shape. When you're importing a SolidWorks model and you're creating, let's say, a finite element analysis, if you have used development module to create, you will have an automatic conversion of the joints. As you can see, there are two different color codes. When you have one or more structural members intersecting or meeting at a point, you will have a magneto joint, and simply means there are more than one structural member. But if it's just a solo, then you can see an olive green is showing you that is a, let's say, insulated sort of joints. The procedure of such a detection is, first of all, automatic, but you have a control over it. Means the joints are by default getting created on a touching face. So there is a hypothetical sphere we're looking at the intersection of the different components and creating a joint there. You can increase the size of this detection to be more and less, and simply merging or unmerging more and less components and creating more or less joints by considering a clearance to your hypothetical spherical sphere of detecting joints. We will be looking at this option on the practical case study, but what we're trying to say at this slide is that you have a control to have more or less joints at intersection, and if there is a gap clearance between the members. And the next thing about the joints are transfer of force and moments to each end of beam elements are controlled at joints. Each beam element endpoint have 6 degrees of freedom. As you can see here, one beam element has 3 translational degrees of freedom and 3 rotational, X, Y, Z. What you are going to do is, when you're creating, let's say, a beam element approach, your structural member is going to be represented by a series of the lines with 2 ends. And now it's your turn to say, my structural member at its end, how it's acting. First, you can say rigid, which you can transfer all the forces and moment from a beam element to a joint. So you have created a joint and you have a beam element. Now we are merging and restricting all 6 degrees of freedom. You can have a hinge type of connection. Well, you can simply translate force, but there is no, let's say, restriction on the rotation, or a slide, which is the vice versa, and also you have the option to manually control the interaction of the beams to the other structural member at their joints by attaching the beam elements at that location. Restriction on first direction or second direction or along the beam axis. Okay. Loadings are all new features when you are using a beam element. You might use, let's say, any face in a solid or shell approach to apply your loads, but in the beams you can have concentrated loads and moment on the joints or reference point. Well, in dynamic studies you can have a time-dependent or frequency-dependent loads, or you can have a distributed load like what you can see in the other picture, which is acting on the whole length of the beam. Gravitational loads can be, let's say, considered by activating gravity. Also, in any dynamic studies, you can have uniform base excitation, or you can have initial condition, well, displacement, velocity, or acceleration at 0 time you can apply on the joints beam segment. Okay, Now, when you have defined your problem using different beam elements, you mentioned you calculated the joints, you set the behavior of the joints, and you attach all your beam elements to the joints and solve the model, it's a time to looking at the result. There are multiple, let's say, properties or factors or criteria we can check after the solution, like uniform axial stresses, torsional, bending and shear stresses into orthogonal directions. We can also get the highest stress on extreme fibers by combining axial and bending stresses, displacement and deformation plots, axial force diagrams for truss and beam, shear and bending moment diagrams, reaction forces and reaction moments for a problem like a beam which is subjected to axial forces and moments in different direction. So all of what we can see in the list can be reviewed and you can make your decision on their magnitude, if it is fail or pass or it's meeting your standard of the design. Now, the last thing I would like to mention here is about truss elements, which is a spatial beam element, which is resist just axial deformation only. Therefore, in the other word, we can say there is no moments are developing in such a structure. As you can see this example, and there is no mechanism. If you have a structure where there is no mechanism of, let's say, transferring the moments, those structure can just go for the beams. Okay? A truss element is defined by two nodes with 3 degrees of freedom, which are displacement in 3 orthogonal directions. So if you have a structure which is just under axial loads, then we can treat them as a truss, and that is also improving the calculation time for us. Okay, now it's the time to look at our case study. The first case study we are going to introduce is a conveyor frame, a simplified model, and there are some operating loads condition on it. Well, you can see we have distributed load of 67,000 Newton on these two components. There is a corner joint we are going to create. Well, we are applying a point load of 45,000 Newton on it and also applying a moment along the direction 1 as 2260 Newton meter of a torque. It has 6 legs. 4 of them are fully fixed and the other 2 are immovable. Well, they can transfer the moment to the ground. But the other 4 are fully bolted to the ground and they are not doing anything else. All right, so it is now a good time to bring our models. So let me switch to this one and have a look. All right. Now looking at our model, you can see this is the model as we said, and if you check the geometry tab, our model tab, you can see all we have created. We used our weldment module to create any structural member, trim them, extrude them, making the end cap, putting the gaskets, and making holes on it. Well, you can see all of these features on it. What is happening at the end? I have a weldment profiles or I have a welded structure. If you have this one and you go to your simulation and create a new study, you can see by selecting any type of study and click OK, you will have a list of your components which has a new icon, look like a beam. That is an automatic conversion as it happened. I can delete the code list and you can see the rest. There is no solid component here or a shell component here. Again, the reason of this automatic conversion is that I have used weldments to create my structure. So I'm not wasting any time. All the cross-sectional properties is being calculated and all the components are being treated as a beam. As you can see, some of them, they've got the eye icon on them, and if you're just standing on any of this, it says an important message. Well, the body is too short to be considered as a beam. The slenderness ratio of the beam, the characteristic dimension, which is depth or width, is less than 10. There is a warning, and it can show you which component it is. Now, as a designer or analyst, you have a decision to accept a bit of inaccuracy at that point and change it to a solid or shell as you might like, or accept this and go ahead. Okay, that's the first thing, and we have nothing else rather than applying a material to series of components we have by right-click, apply edit material to all body, select whatever you want, click apply, or by having a selection like this, holding the shift key and do your selection and apply. Well, you can see all plain carbon steel is being applied to these components. Now it's the time to create joints or edit the joints. Well, you can see this is the difference you get in any studies where you are using beam elements. Joint group, and simply right click, you can see and edit here. You can go and select specific beam to create the specific joints on it, or select the whole beam structure and say calculate. By doing calculate, you can see all the joints has been created. Note that this is an automatic and it is using equal to 0 or touching members. Means there is a joint when this member is touching the other one. And this is the joint. Same here and same here. In so many situations, you might have two members which they are not simply facing or touching each other, and there is a gap clearance. You can make more or less by changing this one and using less than and simply typing the value you like and recalculate. As you can see, as I have created different distance, there are some solo element joints has been created. There is one on this magneto and magneto, olive grain and olive grain as a solo one, and there is one which is simply attaching this top component to the bottom one. So you can have a control about your joints. So I'm not accepting it, and here is my joints. As we said, we have all structural members with their end condition. You can right-click on any of them and edit the definition. You can see this component is treated as a beam. There are two ends, end 1 and end 2. Well, my beam elements are going to stick to those two ends as rigid. Means when this structural member is going to convert it to the series of beam elements, all 6 degrees of freedom at these two ends are going to restricted, and all loads and moments are getting transferred from this structural member to the other one. I can control to make it as a hinge, slide, or manually check this. And say at this joint, these two structural members are acting as what? In direction 1, they can hinge, and in direction 2, they can slide, or anything you might consider. That simply means the structural member which is getting converted to the beam element is acting as you set it up here. The other thing you can control is section properties, as we said here. You can see all the section properties being automatically calculated, and you can look at these properties in a different unit system, or go there and type in any values if you are really interested on changing them. That is a very conscious sort of act, and you have to be aware of what sort of change you are making. Otherwise, those calculations are pretty accurate, and it's looking at the CAD geometry and getting those values with a very good accuracy, as you can see here. So in our material list, we said we can control the end condition for each individual element, how the beam elements are acting, and also cross-sectional properties. Now, since we have all our structure as a series of beam elements, let me go to my study. You can see there is no connection as I said. There is a part. It's not treated as an assembly. And now it's the time to apply my fixtures and apply my loads on them. Well, in order to create a fixture, as you can see, you can have a fixed geometry or immovable as you have the beam elements, any of them. And the procedure is very simple. You will lock to fix on the joint, means that one, that one, that one, and the other one. 4 joints are fixed, means we have fully restricted of the beam element. Do not forget, you don't have any structural member or 3D one anymore. You have a 1D element, and it's going to be fixed at that node or at that point. By clicking OK, it is what we have created here. These joints and this joint are fixed. Looking at the immovable one, edit definition, well, you can see there is no translation, and we have 4 joints, as you can see here. Fixed on these joints is done. Now it's the time to apply force. Well, you can see if you are creating a force. Now in the beam elements approach, you have still vertices and points to apply the force on. You have the option to apply the force on your joints by selecting them like this. And also you can select the whole beam component to apply the force. Your force can be described according to any face or any reference planes, and you can say it's a force in direction 1, 2, or normal, or it could be a moment in any direction. Well, if you have a look here, that's what I've done. Edit definition of the first one. You can see 2 structural members, as you can see in the picture, and there is no force along direction 1 and 2. Normal force to them is 67,000 Newton according to the top plane. There is no moment acting in these 2 structural members. This is a distributed load on the beam, and my other force, as I said before, is considering a joint, which is that corner joint you can see here. According to a front plane, it has a normal of 45,000 Newton load, and it got a moment of 2260 Newton meter on the same long direction 1. So you can add more or less here, or simply not consider them. So I have defined my problem as it was described from the beginning. Now the next step is to simply mesh. Right click, create mesh, and simply you can see my mesh has been created, and right now it is showing us series of 1D elements with the neutral axis, and you can look at this rough estimation. However, you can always go back and ask for render the beam profile and looking at the beam cross-sectional illustration at the same time. Now with all this set, we are ready to go. You can always have a mesh control if you like to have more control over a specific component, or simply ignore it. Now let's run this study, and it is the same sort of approach of other studies, and now we are in post-processing option. In your results section, you definitely can define stress displacement, let's say plot, like what you're doing normally in your studies. Your stress plot, as we said, could be axial, upper bounding direction 1 and 2, upper bound and axial bending, which is the highest stress, torsional, and shear in direction 1 and direction 2. You can always ask for rendering the beam profile and simply have control over the deformed shape with automatic scaling through scale and user define. The other option is look like what we have experienced in the normal FEA studies, showing max and min, have a control over the legend, the position and format, and also the let's say color option, and looking at the secret values, continuous values, looking at the boundary option of model, mesh, and etc., as you can see here. Well, that's the first result I have created, and it's showing me the stresses as upper bound, axial, and bending, which is the highest stresses on the fibers. Well, it's showing us some failure, and we have serious issues at these ends. Displacements are the other options we have. We can look at 4 mm of deflection at the middle point, as we are expecting this. And then from this, we are entering the second type of the result we can create. Define beam diagrams. With that definition, you are entering to a new area where you can access shear force in direction 1 and 2, moment in direction 1 and 2, torque and axial force to be reflected as a series of the diagrams. Now, if I show you what I have created, it is now showing you that diagram. The magnitude and also direction. If we have a look at the shear moment plot on direction 2 on this same component, you can see the variation. Now, based on this illustration, either these magnitudes are within your design criteria or not, you can have more specific, let's say, reports on your beam, let's say, components, and you can go to right-click, list result force or beam forces, and then simply say from element 1 to the last element, from structural member 1 to the last one, which is 16, I would like to look at the force value, and by doing this, you will list all the forces. Well, you can see the first beam is here. Let me have a bit, okay, now it's showing better. That is the first beam, and since that is being segmented to the series of beam elements, these are the segments 1, 2, 3, 4, and etc. As you can see, that is the density of the mesh, and you can look at the axial, shear, shear 2, moment 1, moment 2, and torque on it. Well, that is about this structural member. However, we would like to, in so many cases, that's too much detail of looking at each segment. You can simply filter all your results by showing just extreme values. Means in that let's say structural member, you can see that is my structural member, and the highest values or the extreme values are here. Simply you can select it. Or if you like to just looking at the beam endpoints, what is happening to their connections, that is what you can filter your result. And simply one by one looking at each weld profile or structural members and looking at the values of stress, shear, moment, torsion, and etc. here. Now, as a designer, again, that's your decision of is it good, is it bad, meeting the standard, or it is against it. Okay? One by one, we can switch and review, and as you can see, the graphical area is also getting updated. All right. Now we have concluded the first session. What we learn is how the beam elements are acting, how we can automatically have them in our, let's say, simulation studies, how we applying loads or fixture, and how we review the results. But as we said, in so many cases, there are some geometries where we have multiple components, well, that might be considered with the beam elements or not. Let's have a look. If you remember from a previous slide, we said any beam element got 6 degrees of freedom, and this is true for the shell elements as well. But solid ones, as we are going through all three, let's say, direction X, Y, Z, they just have the 3 degrees of freedom of translation. Therefore, it is highly possible, which if you have a geometry of a solid attaching to a shell or a beam, at their intersection, since you are trying to bond or attach these two components completely together, then the 3 degrees of freedom translational on both type of elements are getting connected and bonded and restricted, fine. But since that shell or beam got 3 rotational degrees of freedom and they are free, therefore it is highly possible to create a hinge connection at the intersection. Therefore, anytime if you are using mixed approach, means we have different type of elements, beam, solid, and shell all together, since we might have a hinge connection, we need to manually go and bound them by doing a contact set, a local contact set, select the components either on the edge or on the face or anything else, and simply bond them together. And the main reason, as we said, solid elements got 3 degrees of freedom and shell elements or beam elements got 6. Therefore, in any case of the bonding, they might create a hinge connection. So this is what we are going to experience and explain how we can control this of looking our case study, and we are talking about this particle separator. This is a particle separator, as you can see. It's installed or mounted on a frame like this one, with the gaskets on the sides and the whole body which is sitting on a couple of brackets. What do we have as a boundary condition? We have installation load on the intake like 75 and 45 Newton. Gravity is active. And we have additional component load on the specific front beam of 150 Newton. Legs are fixed. And now, as an analyst, we have to go and make a decision sorry, which one is using shell elements, which one is solid, and which one are beams. Okay, this is an illustration, and let's go and open up the model now. The first thing you have to do in these cases is to look at your model and looking at the list of the components you have, and if you are a designer, you might have a full control. There is a cyclone particle separator, and there is a sub-assembly of the frame. Looking at these frames, you can see all this is created using solid geometry approach. There is no beam approach. And also looking at the other one, it's showing us a couple of faces, cut faces, and see we have a shell approach here. All right. Now, if we're creating a new study on here, simulation and new study, the difference we can see here is a very significant one. looking at the list of the parts, you can see everything got a solid icon next to it as they have been created using solid geometry approach. Same on here, except a couple of surfaces which is remain. So we have all the geometries in solid. Therefore, in order to create a beam element, we have to convert them. How we can do is very simple. For instance, if you are just looking for a component like that one, and you would like to convert it to beam, you need to just right-click and say treat as a beam. If you do so, you need to get a new communication window. Hang on a minute, where it's gone. All right, here it is. And you see that is a new icon, and you got the joint group icon appeared here. So you can have multiple selection of your geometries by holding the shift key, and make sure you can automatically convert those geometries to beam elements. Okay, now you can see I have converted my components to be treated as a beam. The advantage of creating all this geometry with weldment profile was just to delete or not having or performing this step. Well, now one by one you can go and edit definition, looking at the end condition, looking at the section properties as been calculated. You can avoid this by making a good approach from the beginning. Alright, now let's look at the created study as I have done this stage before, and be looking at the list. Here it is. You can see all my frame components has been converted to a beam component. I have shell on here, here and there. How we convert? We have a webinar on the shell elements, but however I can quickly show you if you have a solid element like that and you would like to convert it to shell. It is pretty simple. Let me find it. Okay, here is my frame cross gusset. Okay, this is the component which currently in solid. I can right click, go to shell manager, or say define shell by selected faces. I can have thin, thick or composite shell, selecting the face, looking at the thickness, probably it's 2 millimeter if I'm not wrong, maybe it's 5, okay, and also the offset. Well, that could be that way, which is not true. The thickness is on the other way. You can see that is the top face of the shell and this is bottom face of the shell. So you're selecting the face you would like to put the shell on, give it a thickness and adjusting the offset. By clicking on here, you can see that is not solid anymore and it got the shell icon next to it. Okay, so you're defining all the shells and all the beams, and the remainings are simply solids. Okay, let's get back to our study and have a look to what we've done. 3 gussets as they are shells, and the frame members which all are beams, and we have these components which are legs are solids. They are not appropriate for shell or let's say beams. And also in a cyclone part, if you can have a look, I have 4 brackets as solids and I have shells here. Alright, based on what you know maybe from before, when we are talking about assemblies, there are multiple parts. And when we have multiple parts, the first thing we have to tell the software is that how these multiple parts are reacting or interacting with each other. That is called contact. What we said, since the elements of solid got 3 degrees of freedom and elements of the beam got 6, at their intersection, that might be a face or let's say edge, we might create a hinge connection. Therefore, in order to overcome this, you need to go and create a contact set, and as you can see, you can have a manual or automatically of bonded between your solid face and the beam here. So what I do, I'm saying this is the beam, and I will create a contact set on the other face here. You can see I have manually bound the face, touching face of my solid component to the beam manually. And if you have a look, there is a big list here. Well, there are some connections between different part of the particle separator as surface by beam or surface by solid, same, let's say, concept, or we're talking about the beams and shells or beams and solids. You can see this is a connection for the side legs, this is the other one, this is the other one, and that is from this solid and this structural member. So what is more than important here is that you need to create all the contact sets locally to bound all these components. Here it is, and that is what I have created. Therefore, either you delete the global contact set, the global role, and keep the local contact set. Now the rest is basically the same procedure as we have done, fixing the legs on their face and also apply the loads. Well, either it's on the face or it is on let's say joints. Well, the first force, as you can see, I have selected the whole beam component according to the front plane 150. I have activated the gravity like here and make it 9.81 meter per second square in front, let's say normal to the front plane. And also my next force, which is getting applied on the shell intake using the face, 2 component 45 minus 75 according to top plane. Okay. Now we've done this stage, our loads are fully defined, and now it's the time to do the mesh. If we need some accuracy at somewhere, well, this is the place on the frame where the loads are transferred from the solid components and the weight of this particle separator to the frame. I've made some finer mesh on these beams, and simply I have created my mesh. So let's create mesh and show it. So this is my mesh, as you can see. Shell elements with no thickness on it, solid elements with a thickness on it, and we have the structural members with a beam element connecting to, again, solids. What we said in this approach is more than important. Everywhere we have 2 different type of elements, like beam and solid, like beam and shell, we need to have a local contact set at those places. Okay, now with that one, looking at the alignments and contact sets, simply we can run the studies and looking at the result. Similarly, stress, strain, and displacement are now available since you have multiple components with a different mesh type. And when you're creating a stress one, you can see, if I go to edit definition, you have to decide. This is a stress plot which is on solid and shells, Well, we're getting back to the normal component of stress, such as normal, shear, let's say principal, and etc. Or it is a beam, which are the components of stress on beams, such as what we have experienced: axial, upper bound, bending, shear, torsional, and etc. Well, there are two different stress plots, and you have to be very, let's say, cautious on reviewing them. So looking at the stress values on the shell and solids, or looking at the stress values, for example, axial on the frame. Well, the reason behind that is that we have different component of stress which is not overlapping in solid shell and beam. For the displacement, you can see the whole displacement on the structure anytime if you like to simply animate it, and understanding the magnitude and distribution of the displacement in your design. And the last thing is, again, exactly what we have experienced before of creating beam diagrams, like the moment about direction 2 on that specific leg, and looking at the values and direction of the change, location of the change. And at the end, you can go and list result force, beam force, or anything else as you might require. Forces or stresses, this time I'm going to stress, and in all my components, and I can again have a look to the list of each individual component and all segments, or simply filter by extreme values. Extreme values on each individual component, one by one. You can see I'm changing, going forward, and the components are getting highlighted in my graphical area. So the result on that specific structural member is that much axial stress, bending in direction 1 and 2, torsional, and the worst case is that thing. Now it's your, again, chance to simply, let's say, accept, reject, redesign, and simply finalize your design here. Alrighty guys, so that is concluding our session today, and there are a couple of tiny things to, let's say, mention again. Beam elements are supported for static and frequency buckling and nonlinear studies. The option of treat as a beam is not available if you have slenderness ratio of a body less than 3 for those structure which is not using weldments. Okay, if you are creating any extrude, revolve, or swap geometries and the slenderness ratio is less than 3, you won't get the option to treat them as a beam. And one important thing, large displacement solution in static studies is not supported for beam at the same time. If you need more information and you have more, let's say, help from us, please get in touch with, let's say, me, svandyar.kuhi@intercad.com.au for technical information, or even go with John Belsham and get a, let's say, initial inquiry, either it's technical or it's a commercial side of it. Thanks everybody for attending, and we hope to see you in the next webinars. Have a good day and bye.